Buenas tardes. Vamos a empezar el seminario. A nombre de la UAM y de la Academia Mexicana de Ciencias que patrocina esta visita del doctor Kartik y del CIATEG, que también participa, CIATEG, Centro de Investigación y Asistencia Tecnológica del Estado de Jalisco, tuvimos la oportunidad de invitar aquí al doctor Kartik Chandran a dar una plática. El doctor Chandran estuvo aquí con nosotros hace 3 años. A raíz de eso hubo un intercambio de un estudiante que estuvo un par de años con el doctor Kartik. Y bueno, esta es la continuación de una relación que lleva ya, pues por lo menos 3 años, muy fructífera, una relación académica, que pues, está abierta eventualmente pues, para continuarse en los diferentes aspectos, sobre todo de las cuestiones ambientales, ¿no? El doctor Chandran es ingeniero químico por el Instituto Indio de Tecnología. Después tiene un doctorado en la Universidad de Connecticut y posteriormente hizo un par de postdoctorados, uno en la misma universidad y luego en Virginia Tech. Desde 2005 es profesor en la Universidad de Columbia en Nueva York, primero como profesor asistente y desde 2016 como profesor titular. Bueno, tiene un número muy apreciable de publicaciones, ciento y tantos, muchas citas, ha sido editor de las revistas muy prestigiosas y ha obtenido reconocimientos, entre ellos el ser MacArthur Fellow, que es muy distinguido en Estados Unidos, ¿no? Entonces, pues sin tanto rodeo, entramos les presento al doctor Chandran, que va a dar la plática, la introducción a la economía circular, el tratamiento de aguas residuales a la recuperación de recursos. Kartik.
Okay, good afternoon. Thank you, Professor Riva, for a very kind invitation to come back here after 3 years, and then also for the introduction. It's my pleasure to share with you all some of the work that we do. I must apologize. In the 3 years, I did not improve my Spanish at all, but I will do so before I come back next time. Okay, so today I'd like to share with you some of the work we do on mostly on this overall. Under the overarching umbrella of resource recovery, and it's really a fascinating, again, it's an umbrella topic which accommodates topics like engineering, social sciences, economics, and more, and health, and so on and so forth. I'm an engineer, so I'll perhaps obviously overlay some of the dimensions that I'm used to within resource recovery. Okay, so before we jump into resource recovery, maybe we can take a few steps back and even identify, let's say, the framework, the questions that we are trying to address using resource recovery. So to do that, I used the slide many times, and so apologies to people who've already seen this. So if you are really to frame the challenges. There are multiple challenges that we are faced with today from a global perspective. So of course we are faced with, for instance, access to energy, access to clean energy, access to energy by itself. Clean water remains a challenge. Access to food, availability of food, quality food is a big challenge, a global challenge. Sanitation for sure, human health, environmental health, education, poverty, demographics, and there are many other lists, and you've probably seen versions of this in many other forms. There's also another big challenge that we are faced with, and that is can you see the bottom of the slide, especially the people at the okay. So what it says here is that there's also another challenge, and that is of growing migration of people to cities, and cities is another global challenge also. People are moving to cities that we know, that we identify, that exist already. And people are also moving towards urban centers that we do not define very well. A very good example of this is Ulaanbaatar in Mongolia, where people are moving towards Ulaanbaatar, but the boundaries they're not very well defined, so we don't even know. We know that this is a city of some form or another, but we actually don't know how this is actually going to look like. So the point here is a lot of these challenges exist, and they are also covered they are also influenced by other emerging challenges. But the point here also is that we've been trying to address these challenges one by one, and we've not treated this as a system of challenges, a system of grand challenges. So what we end up doing is when we try to address these challenges one by one, we end up making more mistakes. A classic example, and perhaps there's connection to Mexico, of course, is that a few years ago, we tried, about a decade and a half ago, we tried to grow a lot of corn to make ethanol for use as a fuel, for instance. And this was I would say this was a mistake of some sort, because of course we made a lot of ethanol, but then we also increased the price of corn and people went hungry because they didn't have access to food. And so this is, when we try to run after one solution one by one, we end up making other mistakes, and then this kind of goes out of balance. The challenge with clean water and sanitation, this is also another example. We try to clean the water down to very, very, very low levels of contaminants. Let's take out all the contaminants, carbon, nitrogen, phosphorus. But then we don't realize, in order to get here, we need a lot of energy. We need a lot of chemicals. And then what happens is that people don't have access to clean water and sanitation. So again, the point here is this is a system of challenges. Almost everything is interconnected. And perhaps we should take a step back and try to develop at least a framework, at least a new set of questions to which that we can answer better. Maybe not one by one, maybe collectively. And that's really a theme that permeates almost all of the work we do as a group at Columbia. Okay, so let's take a look. Given that a lot of work that we do, in the end, comes back to the water cycle. Let's consider what we are doing here today. Let's look at the water cycle globally. Let's look at the water cycle. So I'm going to ask you a few questions now. It's okay. She's not that. It's not that bad. No worries. It's okay. I was going to ask a question. Okay. So let's start here. Maybe I can start with a question. What is the chemical formula of what you're seeing here? Okay, fine, H2O. Okay, that's fine. And this is all good. And the point here is we are getting H2O from different sources, and we are using water for different objectives. I can ask maybe another follow-up question. What is the amount of water that we drink per person per day? Very good, 2 liters. The additional answer I always give is we don't drink enough, but it's okay. It's 2 liters per capita per day. Okay. How much water do we consume? And this varies from region to region. For Mexico, or for Mexico City even, how much is consumed per capita per day? 200 liters, of which we are drinking 2 liters. How much wastewater is produced per capita per day? Probably the same, similar, maybe, yeah? About the same, right? But the point here is we use a lot. We produce a lot of wastewater, but of which we are consuming maybe 1%. When we go to the US, it's not even 1%, it's 0.5%, because the water consumption is a lot higher per capita per day. And then, okay, so keep these numbers in mind, and because some of this is good, we can come back to some of this maybe during Q&A, in terms of do we have to treat everything down to drinking water quality and then use that drinking water to flush our toilets, or can we do something different? Okay, so this is what is happening here, and then what we are doing is we are producing enriched water streams or used water streams, and in some parts of the world we are able to treat this very well. For most of the world we are not able to do anything, right? And so this is what we have. What is the formula here? Very good. Why did you say plus? It's plus, right? We are adding to it. Right? Okay. Is there anything negative about this? For sure, you can't drink this, right? You can't drink this, obviously. And again, my apologies for those of you who I'm subjecting this to again. But this is what it is. This is H2O. This is H2O plus X. All right. Let's come back to this in a few seconds. So let's spend maybe 2 more slides on the water model, on the model for water today. See, if we divide this, and you can divide this into multiple compartments, but let's at least focus on drinking water and wastewater, sewage. So if we look at the model for drinking water, of course there are there are parts of the world which are blessed with piped connection to drinking water, piped sewerage, and everything is great. You open the tap, you get drinking water that you can basically consume, and then you flush the toilet and magically it goes through pipe somewhere else and gets treated. Everything is fine. But this is not the model for most of the world's population. So what do we do? Or what do people do? So this is at the bottom of a big hill. This is actually, I was traveling. And so this is what you see, and this is not what we teach in engineering, right? But somebody knows exactly how big the motor should be, and they have also secured it so nobody walks away, yes? And so they know exactly how big this is. They know exactly, well, they probably pseudo engineered this, the pipe diameter and everything, but they know how to get the water up. And this is all illegal. They're tapping into the drinking the municipal supply. And then as more and more people populate or inhabit these communities, then they have to put booster pumps to get the water even higher and higher and higher, right? So people find a way to get drinking water. They find a way to do this legally, illegally, formally, informally, and so on. So this is what we are doing with drinking water. On the other hand, from the same communities, what happens is you get drinking water all the way up top, but then essentially sewage comes directly out of these households. So this is really. And then you see this everywhere. And so this is very well, this works very well because the drinking water and the wastewater are not connected, but the sewage comes right out, and this is what is happening. And again, this is a classical example of a linear model. Essentially, the model is as follows. We are mining water. In some parts of the world, again, we are blessed with tapping into surface water because everything is connected. Treatment is very good, so the surface water supplies are relatively clean, so you can still clean them, drink it, and then discharge, but that cycle is closed. But for most of the world, this is not possible. So somehow you get drinking water, but then out comes H2O plus X. So this is the linear model. It's not closed, it's not connected. What do we do now? So let's take a look at how things are done in some parts of the world. Okay, let's start here because we have to start somewhere. So when we talk about centralized biological wastewater treatment, sewage treatment, and again, this is very, very high level. So essentially, we take the high molecular weight, the high particle size stuff out, and most of this is done by gravity or mechanical means or adding chemicals and so on. And then we get sludge. For the lack of a better term, we get sludge, and it is really makes little sense because this is really the richest feedstock, the richest substrate that can be biologically consumed. But what we actually feed to the biological reactors are soluble materials, some particulates, but more easily degradable materials. And so what we are actually doing, wastewater, the enriched, the X, H2O plus X, the X can be considered mostly a mixture of organic carbon, nitrogen, and phosphorus, if you're talking about human waste. So we take all of that into these massive bioreactors, and we basically transform the organic carbon and, if needed, based on regulations, the nitrogen and phosphorus. Now let's engage in some more discussion. It'll be good to understand what we are talking about in terms of carbon, nitrogen, phosphorus. Okay, so let's start there. Assuming that this is all human-derived waste. Okay, so we have human-derived urine, human-derived fecal matter. So assuming that this is the case, let's dig into this a little deeper. What is the oxidation state of organic carbon in human waste? This is good to realize. This is good to understand because this then impacts what we are actually doing with it, or what we should be doing with it. What is the average oxidation state of organic carbon in human waste? -2. So it's good to recognize also we have 8 electrons to play with, right? So it's +4 is CO2, -4 is methane. Okay, so on average, what should be the oxidation state? Should it be +4? It's not CO2, right? It's not CO2. It's obviously not methane. It's somewhere in the middle. And if you take an average, considering what we are made of, the average oxidation state is close to 0. Look at carbohydrates, look at lipids, look at proteins. The average oxidation state is close to 0. What is the average oxidation state of nitrogen? Let's say there are proteins, amino acids. We're talking about -3. -3. Good. Phosphorus is +5. Okay. What are we doing to carbon 0? What are we doing to nitrogen -3? What are we doing to phosphorus? again, if we are able to, if we have access to energy where we can aerate everything and oxidize everything, we basically convert the organic carbon into CO2. And nitrogen, depending on the regulations, we can convert it to nitrogen gas. That's also oxidation, right? -3 to 0, that's oxidation, right? And then we've removed it. Phosphorus we can precipitate out and do other stuff. So all of this has happened. Then we produce more bacteria here. We settle the bacteria, put it back into the reactors. Depending where we are in the world, we can disinfect it and discharge it. What have we obtained in return? We obtain clean water. Now, all of this comes at a pretty significant cost. The energy that we have to provide to oxidize the carbon, to oxidize the nitrogen is quite substantial. We also need to invest a lot in terms of chemicals to drive some of these processes. And then in some cases, the organisms that we are dealing with, the reactors that we're dealing with, can also produce greenhouse gases, which could be quite substantial. Okay, let's put some actual numbers. If we are talking about really, really inefficient but very good treatment processes, but which are inefficient in terms of energy and chemicals, we are talking 60 cents to $1 per pound of nitrogen removed. Okay, close to it. Even if we say 50 to 60 cents per pound of nitrogen removed, this is quite substantial. This is quite substantial. In terms of chemicals, at least close to where I am right now, we spend about $20 to $40 million just purchasing organic chemicals to remove nitrogen from the wastewater in New York City, and that's quite substantial as well. And what have we obtained? We have obtained clean water. Going back to the grand challenges, we have solved the challenge of water, but just the challenge of water. We have no accounting of how much we are spending. We don't pay much attention to how much we are spending in terms of energy, in terms of chemicals, and so on and so forth. And that's fine, it works, but what really goes wrong is when we take these models and put them in parts of the world where they are never meant to be. So let me show you another example. So this is an upflow anaerobic sludge blanket reactor, USB, very common in tropical countries around the world. And this is a massive USB type system in the city of Accra in Ghana. And this is actually, I've been to this plant many, many times. It's a nice plant. Doesn't do anything. It doesn't do anything. It's just sitting there, and the reason is because it's not because the technology doesn't work. USB is a very mature technology. It works very well. It doesn't work because it doesn't get the waste that it is supposed to treat. And so we take these technologies and totally, we do not consider the externalities that need to be considered to make an overall ecosystem work, not just the technology. And I'm a pure technologist, but even I'll be the first one to admit that technologies are not the limiting factor here. Okay, and so let me tell you maybe in 2 minutes what the story is over here. This is the Atlantic Ocean. This is a picture I took when you go out. You go out and then you come back in, as we do in many, many parts of the world. So what happens is, this plant is supposed to be fed with trucks that come in with fecal sludge from the greater Accra metropolis. And so what happens is that Accra also don't have pipes. They don't have pipes for drinking water. They don't have pipes for fecal sludge to convey the fecal sludge into these plants. So the trucks come in, they empty the tanks, and they take them to plants like this. Accra, like many cities in the world, is also subject to variability in terms of traffic. The truck drivers are paid based on the number of trips, not delivered to the plant, but emptied out of the households. Okay? So then the truck drivers don't want to sit in traffic, so they just bypass the city and dump all the sludge here. You can see this. This is a plume of fecal sludge where this is actually they have figured out there's a very formal site for dumping. This is, that exists. Unfortunately, across the highway is the plant. So this is the disaster here. So the plant is there, technology is there, and the fecal sludge is in the Atlantic Ocean. And just because we have neglected some factors. So you cannot see this, right? Especially at the back. Okay, I will read this. So this is not the only factor that we ignore. There is also energy. So maybe I'm exaggerating a little bit, but I'm giving you real numbers. So first I have the United States, and here I have the energy consumed nationally in the US. And the value here is 2.4 teratons of oil equivalents. Okay, it's a large number. 330 million people, this is the amount of energy that's consumed. A fraction of that is devoted to the enterprise of clean water, drinking water, wastewater, pumping, treatment, everything. So it's 3 to 6%. Even if I take a low number of 3%, I have the number of 0.07 teratons of oil equivalents devoted to the enterprise of clean water. Let's go to Ghana. This is where we are. Let's go to Ghana, and even if you normalize, the population there is about 80 million people. They don't even have the energy that we can expect them to take, especially all these technologies from other parts of the world, and expecting to put them here and run those technologies. They just don't have the energy. And just to give you an example that is from a very personal standpoint, I grew up in Delhi in India. We did not have energy 24/7. I remember sitting writing exams when the temperature was close to zero, and what happens is your handwriting becomes smaller and smaller because it's cold, your hands are freezing. And then you get 40 degrees Celsius in the summer, and then there's no electricity. We did not have access to clean water 24/7. We had access to water 3 hours a day. So we also had illegal pumps, and we boosted the water and stored massive amounts of water. But this is reality and it's not just clean water and sanitation. This is reality for about 4 billion people on the planet. And so now if you ask those people to take the energy, the little energy that they get, and devote it to models like this, they are absolutely not going to do this, right? So we need better models. We need to totally change our thinking. And so the model that we have now, let me go back one slide. This model that we have now, we take H2O plus X, and we put more energy, more chemicals, more resources, and what do we get back is H2O to meet a certain set of permits or regulations, and we've devoted some resources here, and that's not possible. So what do? Let's go back to the blueprint. Instead of putting in more, perhaps we can consider recovering the X, not removing the X, but recovering the X in the form of chemicals and energy. And chemicals, I think we really have to pay attention. It's not just energy. In some parts of the world, energy is not the appropriate endpoint. It's chemicals. It's other products. We can recover this here instead of dumping the sludge. We can do this, of course, in the bioreactors. These are the factories where we can recover a lot of this. Let's look at the flow. And as I understand it, there are plants in Mexico City, single plants from which there is a huge flow of wastewater. And after treatment, we can recover some of that energy as well. We can recover chemicals and energy as well here. And the point here is, what am I missing here? I'm missing clean water, because if you do this properly, you can produce clean water not as the sole product, but as the byproduct, and the byproduct of all of this. So now we are not talking about wastewater treatment anymore. We are talking about biorefineries that take not just sewage, they take all sorts of other waste, agricultural waste, industrial waste, and so on. And so these are basically refining not just carbon, but nitrogen and phosphorus down to different up to different endpoints, and of which water is one of the many products, not the sole product. And this is a model that can be perhaps adopted. And just to give an example also, in terms of what we are dealing with, just for the city of New York, we are treating about it's close to 1.3 billion gallons of sewage per day. And what does the sewage contain? It contains about 2,000 tons of organic carbon per day that can be recovered, not removed, not converted to CO2. It also contains about 300 tons of nitrogen in exactly the same oxidation state that we needed for plant growth. It also has about 60 tons of phosphorus. So instead of taking all of this and removing this, perhaps we can start to recover some of this. This 300 tons of nitrogen per day, if you multiply it by $0.5 per pound of nitrogen removed, you can try to figure out the cost. And this is also why we need more efficient technologies that can use less energy, use less operating capital for operations as well. And then I would urge you perhaps to do the same kind of calculation for Mexico City or other cities to figure out what should be done, what can be done, and how it should be done. Okay, let's spend maybe just one more slide on energy and try and at least make the case just to see if this is even feasible. So I'm giving you two numbers here. One is the energy present in the carbon in wastewater, and I'm normalizing this to million gallons. So the way I arrived at this number is, if I take just the organic carbon present in human waste, diluted in the form of wastewater, if I just take that organic carbon, convert it to biogas, so not carbon zero, not to CO2, but to methane all the way back, so -4. If I take all the organic carbon, convert it all the way to biogas, take the biogas, recover energy from it, this is the amount of energy that I can recover. And of course, this is not going to be very efficient, but this is what we have. Now, let me go to the other end of the spectrum. If I now use the least energy efficient processes to treat that wastewater to the highest degree, remove the carbon, remove the nitrogen, remove the phosphorus, right? The least favorable alternate, I have this amount of energy that I need to put in. So if I'm using the least favorable endpoint, if I'm using the least favorable technology, we are still breaking even. Now, if we start going beyond biogas, if I say I don't want to work with biogas, let me go to higher value endpoints, higher energy endpoints, next generation biofuels, this number is going to go up. If I now start focusing on technologies which are more energy efficient, this number is going to go down. So now the balance is going more and more and more positive. Okay, so this is not science fiction, this is reality. If we now stop thinking about wastewater treatment, pollutant removal, if we now start to look at recovery of resources, including water, it doesn't have to be potable water, including water for different objectives, this now becomes more and more favorable. So let's take a few examples now, and that's what I'm going to spend perhaps the rest of the time today. And so what can we do in terms of end products? We really have to stop thinking about biogas. We really have to start thinking about other endpoints beyond biogas just for the carbon. The nitrogen and phosphorus we can think as well. And I know many groups here are actually working on this. Professor Reva himself is working on this, going beyond biogas to far higher value chemicals. Of course, we have to figure out the market. We have to figure out the economics. But we really have to stop just fixating on biogas. What can we do? We can look at high energy, next-gen biofuels. We can look at commercial chemicals. Nutrients, of course, can be recovered for fertilizer as well. The other thing that I always stress is that we should really, again, stop getting carried away. Just because we can make biofuels, just because we can make high-value chemicals doesn't mean we should. We are not in this enterprise just to extract chemicals that have no end application. These resource recovery really needs to address a higher objective. And some of the work I have done, the objective is just providing sanitation. Okay, that's the higher objective, which is then supported by some of the resources that we are able to recover, and that I will discuss as the first example. So the first example I want to give is the work again back in Ghana, where the objective was to convert the organic carbon present in human fecal sludge to lipids and to biodiesel. And the point was not to make biodiesel just to sell at a pump. No, the point was to run the treatment plant processing the fecal sludge on the biodiesel that we were recovering. So it's basically producing something but using it within the boundary. So those inefficiencies of extraction, transport, and so on are taken out. You're using it right there. So let's take, so the objective here is fecal sludge to lipids, and I'll come back to why I underline and highlight the two, lipids and biodiesel. So let's take a look at what biodiesel is. So human waste, of course, has organic carbon. It contains carbohydrates, it contains lipids, it contains proteins as well. So the fat that we have are basically triglycerides. What is a triglyceride molecule? It's basically a glycerol molecule with long-chain carboxylic acids. Okay, what is biodiesel? We take the lipids and we transesterify them with methanol. So then what happens is that the glycerol gets kicked out, the alcohol and the carboxylic acid get esterified, and the fatty acid methyl ester is now biodiesel. That's biodiesel. Okay. And what are lipids? I already explained this. So this is basically a glycerol. It's a triol glycerol, and then we have the carboxylic acids. Okay. So initially the objective of this project was not fecal sludge to lipids. It was basically fecal sludge to biodiesel. And they even came up with a nice acronym, and then we realized it's not the most efficient. I'll come back to lipids and fecal matter later on because I have this nice picture I can show you. So this is human fecal matter. It's mostly water. This is to be expected. And then we have the other stuff in here. The initial objective of my project was to take the fat, the lipid out of the human fecal matter. Okay, I take the fat out, react it with methanol, and that's it. I get biodiesel, right? That's it. But the point is, when we go do a lipid panel, I'm going back one slide, the lipids present in human fecal matter is very, very, very low. It's about 6 to 10% on a dry weight basis. So 6 to 10% of this is this lipid fraction. So if I want to do this, react with methanol and make biodiesel, I'm going to get a very, very, very small amount of biodiesel. We didn't stop. Of course, we realized that this is the limitation. We didn't stop. What we then figured is, if we can take all of this and convert all of this to lipids, then we have a higher mass of lipids that we can actually work with. We can produce a lot more biodiesel, and perhaps this becomes more favorable. So our technology basically doesn't focus on the inherent, the intrinsic lipid fraction. We basically take everything and convert it to lipids. Then the question is, why do we stop there? We can take everything and convert it into carbohydrates. Take everything, convert it into other organic molecules, right? So now this is biorefining. It's just not just scavenging the lipids and making biodiesel. This is now truly refining, taking a mixture and making basically anything that we want with it. This is more powerful, and that's what we did. Okay, so basically the platform technology that we have is, we take basically any waste, these are all enriched streams, we channel this through an anaerobic fermentation platform to make short chain volatile fatty acids, and then we use those volatile fatty acids to go anywhere. So we've done lipids, we've done some other compounds as well. And so the point is, the challenge I think today is to basically understand what we can make with the VFA. That's really how powerful this technique is. Once we make the VFA, we can, I think, go many different endpoints. So let's now understand what we need to do in terms of producing the VFA. So for that, again, let's go back to this conventional model of anaerobic digestion. So anaerobic digestion, as we treat it, is essentially a cascade of multiple processes. The first 3 steps are catalyzed by bacteria. The last step is catalyzed by archaea, and traditionally the last step, for most engineered configurations, the last step is the rate limiting step. It's the slowest step. So if you want to accommodate the slowest step, you have to provide a long retention time, right? And so the retention time typically employed even at mesophilic temperatures is close to 20 days. So essentially we need a long hydraulic residence time or a solids residence time, and this is what we need if we want to produce biogas. Now there are also other endpoints that I'm going to focus on, and that's not biogas. They are the precursors to biogas, the short chain volatile fatty acids, for instance, acetic acid, propionic acid, butyric acid, and so on. So what do we need to change if we don't want biogas, but we want some of these intermediates? So that's when we talk about anaerobic fermentation, not digestion, but fermentation. And so basically, if you want to take the last step, which is the slowest step, you can design a process with a much lower retention time, a smaller reactor. So by doing that and a few other controls, you take out the biogas. Now biogas, again, just to emphasize this, is not all methane. It's a fraction which is methane. It's got CO2, it's got other gases, it's got moisture as well. So it's not trivial to use biogas if you want to recover high value energy. So, but we know how to make biogas, and perhaps that's why we do it. But there's a lot more potential if we don't go all the way to C-4, but if we stay close to, well, let's say we don't allow it to go to C-4, we just basically take the acids, and we can do a lot with the acids. And the other advantage is we have smaller reactors, or for the same reactor volume, we have a higher throughput. Okay, so now let me take you to the results. So for this project, we actually, now the focus is extracting the acids, making lipids, and then making biodiesel with the lipids. And this was done in the city of Kumasi. And so we were working with the Kwame Nkrumah University of Science and Technology, which is in Kumasi. So this is Ghana. This was our system. And so the objective was to basically convert the fecal sludge into biodiesel. I'll skip through this. And this is the system that I designed. So let me show you some pictures. So this is where we are. Actually here you can see some of, this is basically a dump site for fecal sludge. It's far away from the actual city. There's no water, there's no electricity, there's no Wi-Fi, there's nothing. But there's a very, very steady supply. Every 2 to 5 minutes there's a truck of fecal sludge coming in. That's guaranteed. There's nothing else, but there's a lot of fecal sludge. It's a dump site. And so here you have anaerobic lagoons. Here you have also mountains of fecal sludge. So we are surrounded by fecal sludge. And so we actually built this whole system from scratch. And so these are the tanks. Each tank is about 10, is actually 10 cubic meters, and there are 12 of these tanks. Okay? So essentially we are taking fecal sludge that comes in, we have the receiving tanks, and we have a splitter box. And the hypothesis here was, I basically staged these reactors so the fast reactions can happen, and each tank is about 2-day HRT. So the fast reactions can happen here in the first upstream tanks, and the fast reactions are the ones producing the acids, and then the latter tanks can produce the biogas, the methane, right? So that was the hypothesis. Okay, so we had all of this, we ran the reactor, and this is our approach. We ran the reactor for close to 9 months or so. We took the data and we did some process modeling, model calibration, and then we have a model now that we can use, and these are the details and so on. And we did a lot of measurements from multiple reactors over time. We did a lot of measurements that are not typically done with the wastewater industry, not with fecal sludge. Nobody does this for fecal sludge. But the point is, we are not running a fecal sludge treatment unit. We are running something where we want to produce biodiesel. So we obviously have to start measuring a lot more. And so we translated the design into a process model, and for the first few months we did not have balancing of the load or the flow even. So this is the variability. After that we were able to balance this a lot better, and our process also started doing this. Just to give you an idea of what fecal sludge actually is, just in terms of the coarse parameters, this is the variability that we are looking at. Huge variability. We can't stop because we have variability. We have to just design our process that can handle the variability. That's the point. Okay. Sometimes what happens because of the variability, this is tank number 1, 2, 3, 4, 5, 6. There is so much production that the tank overflows. So this is a mixture of processed and unprocessed fecal sludge, but that's reality. And so using all the numbers we had, we actually calibrated the process model. The process model is basically a set of equations that describe the multiple steps of carbon conversion. So there are probably thousands of parameters in this process model. And I'm just showing you a very tiny sample data set. So this is reactor 1, 2, 4, and 6. And then here I'm showing you the dots, which are the experimentally measured values of the total VFA, off-gas flow rate, and then the red lines are the process modeling outputs. The calibration model, calibration approach is basically to match up as well as possible the model and the experimental results. And so if you want a perfect match, you can go and change all the parameters, put it into a data mining software, change all the parameters, and you'll get a perfect match. But this will be meaningless. A good calibration exercise, if you truly understand the process, change as little parameters, the values as possible, and still get a reasonable match. And so for our calibration effort, with all those thousands of parameters, we only changed 7 parameters, basically, and we were still able to get a good match. And the point is, now we have this process model that allows us to describe the fate of fecal sludge through this cascade of reactors to produce both biogas and volatile fatty acids. And I'll tell you right now that the hypothesis that initially all the reactors will produce here, the upstream reactors will produce the acids and the downstream reactors will produce biogas was not valid, because fecal sludge is not inert. It comes in already with bacteria, it comes in probably already with archaea, and they are active. It's already getting processed when it comes in. So even at a 2-day retention time, we get biogas production, because this is not dead material. This actually, it's actually active. And all of this had to be considered during our modeling approach. But the point here is, this was the first model for fecal sludge conversion, not just to biogas, but in a very systematic fashion, conversion to VFA and methane. Now we can extend it if you're now talking about pit latrines and other processes, other interventions. Okay, so that was one of the results, and and the project was quite remarkable, because we were told not to do any lab scale work. We were told basically to go out to the field, and at a scale that was actually reasonable. So that system, the 120,000 liter system that I designed, was for close to 20,000 people. Okay, if you imagine building a plant for 20,000 people using the conventional centralized model, the plant would have been orders of magnitude larger in capacity. And that's because of that dilution factor. 1% of the human waste 1% of the water we drink is pretty much the waste that we produce. Okay, 2 liters on average, because we're not expanding because the waste is accumulating. But then we produce 200 liters of sewage. And that's the amplification factor. Now, if you take that out, your plants are a lot smaller. And you can make them more efficient, not by going to biogas. You can really make them a lot more efficient. And that's the point. Now, what are the outstanding research gaps? Of course, we have this. This is great, but we don't stop there. What else can we learn? What else do we need to do? I showed you the cascade of anaerobic carbon conversion. But the point is, we don't even understand how to convert the organic carbon to volatile fatty acids completely. We have a pretty good understanding, but it's not complete. And so that's something that we are working on right now, because this is where we want to stop. We want to produce volatile fatty acids, but we want to do so in a controlled fashion. We want to be able to produce the right amount of acetic acid or a defined amount of acetic acid, propionic acid, butyric acid. We want to maximize the conversion. We want to maximize the yields. And we don't want to sit there and measure 20,000 different components in the feedstock. What we want to do is, if I am given the fraction of amino acids, the fraction of carbohydrates, the fraction of lipids in my incoming organic feedstock, I need to be able to predict what I can do in terms of my effluent VFA speciation and the yield. This is what I need to do. So this is real bioprocess engineering, and this is the black box that we are now trying to open up. And so in this project, we went kind of in the reverse fashion. We went to the field and came back into the lab. Now we came back into the lab and ran some reactors. I'll get to this in just a second. So we cannot use fecal sludge in some of the labs at Columbia, so we use food waste. And we fed reactors with food waste. These are continuous reactors again, long-term reactors, run over a year or so. And we did 6 reactors. So these are the 6 reactors. So there are 3 sequencing batch reactors, and then there are 3 step feed reactors running at 3 different retention times: 2 days, 4 days, 8 days. Okay, 2 reactor configurations and 3 retention times. And what I'm showing you here is the overall metagenomes of these 6 reactors. If I know the sugars, the amino acids, and the fatty acids, I would like to be able to describe what happens to these components as they are converted to the volatile fatty acids and ethanol. So that was the objective here. So it's not a black box. I'm not putting big black boxes here. I'm basically opening up the individual reactions. And for each of those reactions, this is not conceptual pathways that you look at in a process engineering book or a microbiology book. What I'm showing you here are the results for each of these pathways, for each of the 6 reactors. That's what I'm showing you here. So the darker the color, the more represented is a given pathway in a specific configuration for a specific HRT. That's what I'm showing you here. So basically what I'm showing you, for example, for fatty acids, this overall cycle, the beta oxidation cycle, is very well represented, right? Because these are dark colors. If you look at some of these other symbols, they are very light or they are white. It basically means that those pathways are missing in those reactors under all conditions. And this pathway is basically for formic acid production. Formic acid is a one carbon carboxylic acid, and we never detected it in our system. And sure enough, those pathways are completely missing. Okay, so that's the level of understanding that we have to generate if we want to be able to describe, if we take sugars as a feedstock, proteins as a feedstock, lipids as a feedstock, and if we want certain defined products, we want to be able to understand what is happening. This is done at a DNA level, so this is metagenomics. If I do it at the RNA level, this will be metatranscriptomics, and from metatranscriptomes, I can get activities. So once I get the activity and the potential, now this is a totally different system I'm looking at. I can model this. I can do different things. So this is truly opening up the black box. We don't have to do this for every system we run. This would be impractical. But once we understand the system, then we can connect the arrows, feedstock to product. Ultimately, that's what we want to run. We don't want to run black boxes. We want to run real engineered reactors. Okay, so let's keep going. So we know how to make VFA. Let's say we make VFA. What do we do? after we concluded our project for biodiesel, we realized that maybe we should not be making biodiesel, maybe we should make lipids instead. So now I'm going to share with you very quickly how we make lipids. So basically we make VFA, and how do we go to lipids? We basically use a yeast platform to convert the VFA into lipids. There are some advantages to doing this. I won't focus on that now. Maybe I can do that during Q&A. I'm going to run through this, skip this. But essentially, it's good to produce a lot of lipids. It's good to produce the lipids quite quickly. But so kinetics and yields have to be high. But we also have to make the right lipids. So what I'm showing you here is the lipid profile expressed as a percentage of overall lipids for many different sets of conditions in terms of carbon to nitrogen ratio in terms of different feedstocks. So this Cryptococcus albidus, the yeast platform, is basically, if you take a step back, forget about the numbers, take a step back, look at the profile. The profile is remarkably consistent across different conditions, across different feedstocks. So this platform is basically coming up with a consistent lipid profile. Now we of course have to identify what this lipid profile actually means. This lipid profile essentially corresponds to that of palm oil and soybean oil. So for our system, what we are actually doing is we are basically producing palm oil and soybean oil not by growing palm trees and cutting the palm trees, not by growing soy and harvesting the soy. We are basically producing palm oil and soybean oil from food waste. So that's the other connection. We are disrupting the linear model, growing palm trees, cutting the palm trees, getting oil, and that's it. Done. We are mining palm oil. Same thing with soybean. Same thing with the model that we grow food crops and produce biofuels. Here we are taking food waste and making certain end products, and that linear model is again getting disrupted. And so this is something that we are quite happy with as well. Again, proceeding more in terms of discovery and research and so on. We are not stopping in the field. We are not stopping when we make soybean oil or something. We keep going, right? And so what were the outstanding research gaps? We realized that the Cryptococcus albidus genome was missing. Why do we need to do this? Again, we don't want to take this as a black box and basically work with it. We want to open up these systems and then engineer them better. And so we sequenced the genome of this organism a couple of years ago, and we now have this genome. We know that this organism accumulates lipids. It can accumulate probably carbohydrates, proteins. It probably can make other stuff as well. But for that, we need to understand what the potential is, and that's what the genome gives us. So we don't sequence genomes just because we can do so. We want to take this information and engineer better processes. Economics, people ask me what if this whole fecal sludge to biodiesel even makes sense. Well, the answer is yes. Even now it makes sense. If you take fecal sludge and want to go all the way down to biodiesel, this is the cost of production. So it's 81 cents per kilogram of biodiesel produced. So even for many markets today, even in this environment, this is favorable. But the point again is we are not making biodiesel to sell at a pump. The point is we are taking that biodiesel and running a sanitation facility. We are treating fecal sludge with it. So we are basically going from a dump site where there is no fecal sludge treatment, so 0, and we are going to treatment. So it's going from 0 to 1. So the cost, I would say, is somewhat immaterial because we are addressing a higher objective. Okay, what else do we need to do? We need to understand what fecal sludge is. We have to stop thinking about this as 75% water and X. So this is something that we are working on now. We are working on a project really taking samples all around the globe. What is fecal sludge globally? So again, we are looking at the chemical composition. We are doing some sequencing work on it's called the global, what is it called? The Global Fecal Sludge Microbiome Project. And that's what we are doing. We are trying to understand the microbial composition, the structure, the function, new pathogens, antimicrobial resistance signatures. All of this we are looking at in fecal sludge samples from all around the world. Treatment is just one of the objectives. What else is there? Can we infer human health from the fecal sludge samples? So that's what we're doing here. Okay, this is just a slide that shows what we can do with VFA. So these are all the different streams. Anaerobic fermentation produces VFA, and the point is we can go just about anywhere with the VFA. I just showed you one example. You can go just about anywhere. And this is a review article that a postdoc from UAM, Luis Arellano, he's working on now. So I thought I'll share that. We can do many, many different things with VFA. We can use the VFA for treating wastewater. This is one of my first projects in New York City, 2002. We can make bioplastics. We have done this. Other people have done this very well. I'm not really sure this is very, very favorable right now. This is the technology actually that we are quite excited about. This actually can be implemented. So we actually use, we don't stop at VFA. Even if we make dilute biogas mixtures, we use a different process where we use ammonia oxidizing bacteria to convert selectively the methane in biogas to methanol, and the ammonia oxidizing bacteria also oxidize ammonia to nitrite, and when coupled we can basically have a very efficient denitrification process. So going back to the example I mentioned, in New York City we spend about $20 to $40 million purchasing methanol, glycerol or other carbon compounds, and then we also take the biogas and flare the biogas. So again, we make biogas, dissipate it, and then we bring organic carbon compounds to treat the wastewater. With this technology, we take the biogas and make chemicals, and we are able to reduce or eliminate the organic carbon that we need to bring into the boundary, and we achieve nitrogen removal. So this is again one of those, again closing the loop, making this a bit more circular. Okay, we don't have to, I think I will run out of time, so sorry to skip. Basically the point of all of this is methanol is everywhere. We should probably start taking a deeper look at methanol and not just at some of the other alcohols. And these are some fundamental details in terms of how we produce methanol using ammonia oxidizing bacteria. Sorry, I'm jumping ahead. I can come back to Q&A. I just want to allow some time for questions. Okay. Now I'll give you maybe one or two examples of things we should not do when we look at resource recovery. We had this very exciting project funded by the Department of Energy, and this was based on CO2 capture from the atmosphere and underground storage. And so my colleague was working, maybe I pressed something I should not have. My colleague was working on using serpentine for capturing CO2. So I don't have control on this. Yeah, that's fine. So I think the window is right there. Yeah. Okay, great. Okay, thank you. So here the project was to basically use serpentine to mineralize the serpentine and then use the cations to pull in the CO2. And the point was, how do you mineralize the serpentine? Yeah, so this was the process technology. So you take rock and you add some weak organic acids and you mineralize the rock. And then once the cations are released, then you can adjust the pH and pull in the CO2, and this is to sequester the CO2. So this is geological CO2 sequestration. The concept is great, and where my tiny little contribution was to produce the weak organic acid, so take organic waste, ferment it to VFA, and use the VFA to mineralize the rock. This is a great project. It's a very nice application, but it's not very practical. But the point here is, at that time it sounded like a very nice connection to make. And one of the things I'd like to also suggest is, I think we do a good job at learning the fundamentals, but I think if we truly want to have impact and want to do some nice cool things, it's always good to look to connect to other disciplines, other topics, other end applications, and I think that could lead to very nice, interesting stories. This is another project again from the Energy Department, and here what we are doing is we basically have a process that using ammonia oxidizing bacteria that oxidize ammonia to nitrite, and these are autotrophic organisms, so they fix CO2 and make more biomass. But our application was for these organisms to take CO2 and make isobutanol, Why isobutanol? Because it's a very, very high energy product and commercially quite favorable. So we basically took a product for taking some biomass precursors within the cell and making isobutanol. Again, very interesting. From a very fundamental perspective, this is the first time this was ever done in this organism. But there are some limitations here. The precursor for isobutanol, isobutylaldehyde, is toxic, so the organisms don't like it. These are autotrophic organisms. They grow very slow. The yield is very low. So if you put a heavy plasmid with these pathways, they just don't like it. So it's a very novel application, but practically not very useful. So again, this is part of the journey. So, but I have one more slide after this, by the way. So where are we right now? So essentially, if we want to truly harness the potential and make a lot of these systems circular as opposed to linear, the water model, the model for water, energy, food, and so on, we really have to start addressing these as systems and not individually. And once we start to do that, we are able to now consider the X as something, not something as something that we have to remove, but as something that we should recover and we can recover. So it's, again, technology is not the limiting factor here. We need to be able to figure out what to make, what to recover. So for example, if I'm sitting in the middle of Africa, do I need to produce isobutanol? Absolutely not. Perhaps I should do something that actually helps with a challenge that is locally more relevant, and scale also comes into this in a big way. The point is, we can make just about anything. We need to understand what to do and how to do it. And so for this, we need to understand links to higher objectives, not just from a technology perspective, but to some of those grand challenges that we have. Finally, I'm going to just provide you with a somewhat, it's entirely a qualitative, probably a very subjective framework, but perhaps we can indulge in this discussion for the next 5 minutes. So what I have here is the world broken down into the developed, underdeveloped, and developing. Again, as a qualifier, these maps are from Wikipedia. Mexico is not on any of those. Russia is on all three, and there are other countries which are also misrepresented. So with that qualifier, let's look at a developed, according to Wikipedia, let's look at the developed world. What I'm going to ask you are a few questions in terms of, should we protect human health? Should we recover nitrogen? Should we recover phosphorus? Should we make fancy chemicals? So let's look at the developed world. And let's look at some of those challenges, for instance. Let's look at food security. Let's look at engineering education. Okay, so if you look at the developed world, food security is good, so it's in green. Education is mostly good, so it's in green. So having these two filters, let's look at the questions. Should we protect human health? Oh, the answer is always yes. Always protect human health. Should we recover phosphorus? The answer to this is yes, because phosphorus is a limiting resource. At some point, we are going to be, we won't have access to readily available phosphorus, so maybe we should have this green. Should we recover chemicals? Should we recover not fancy, should we recover high-end products? And the answer is yes, because that can be supported by the education, the technology advances, and so on. So this is the fingerprint of a developed community. Okay, let's start there. Let's go all the way to the other end of the spectrum. In terms of challenges, this is a big challenge in many underdeveloped communities. Food security is a big challenge. Okay, let's ask the question, should we protect human health? Absolutely. Should we recover phosphorus? Should we recover nitrogen? The answer here is yes to both, because this can impact food security positively. The answer here for nitrogen was maybe, because we already have ample food security, and in the developed world, perhaps there's not enough incentive to recover nitrogen if done alone. If it comes out with then yes. So this is a maybe, but in the underdeveloped world, both are yes. Should we produce isobutanol? Probably not. And this is also, there's also another challenge here with education that needs to be reoriented. And maybe we stop with conventional education teaching wastewater treatment. Maybe we start with other new directions which will actually have a societal impact. Maybe we can start with wastewater treatment and go somewhere else. We still need to teach wastewater treatment. Okay, now let's look at the developing communities. Food security is not as bad, not as good. So there's still some opportunity here. So again, yes to human health, yes to phosphorus and nitrogen because we can still convert this light green into dark green. But here, I think we can do everything because there is also good foundation in terms of education. And so I think this is perhaps the most exciting part where we can do a lot more than some of the extremities. So this is useful for me because it allows me to at least frame what I'm going to do with the technologies in terms of which technologies, which endpoints, addressing some of the global challenges, not just the technological challenge. Okay. So as usual, I think I've taken much more of my time. So if there are questions, we can address them now. Thank you. This is stuck.
¿Preguntas? Si no se animan en inglés, pueden ser en español y aquí Flor las traduce. Changing the paradigm from water treatment plants usually use mixed arsenic culture. And then if you want to go to specialized products, you need to change to perhaps pure culture. So how do you conceive this change? No?
Yes, and this is indeed a change in the paradigm, and this is a refreshing paradigm. So again, when we talk about conventional wastewater treatment, we deal with mixed communities, and the model has been, let's continue to work with mixed communities, but and that's fascinating. We do a lot of mixed community work, so probably also a lot of you. But the point is, if we truly want to mine for the highest value products, the highest value endpoints, I think at some point we have to change to monocultures, to even engineered cultures, where we can truly control what we are making, the rate, the yield, and the product type. And I think that's the wave. And so when we talk about even our fecal sludge to VFA to lipids, the first step can be mixed culture. Anaerobic fermentation, a big tank with everything, and we're producing a mixture of VFA. We can pass those VFA through a membrane either for sterilization or for selective capture. And then what comes out can be fed to an industrial fermentation process where we make lipids or carbohydrates or other chemicals as well. So it could very well be a hybrid model where part of the treatment is mixed culture, but part of the recovery is then high-end biotechnology. And the other model that feeds in is maybe these wastewater treatment plants are not really doing these new processes are not just wastewater treatment plants, just processing sewage. Maybe this is a co-localized facility, a co-localized biorefinery, of which wastewater treatment is just one of the components. Maybe this is where there is food waste coming in, ag waste coming in, and so on. And I had the pleasure of seeing this facility, a pilot plant at the Iztapalapa campus, where the wastewater comes in from the university, but then, as I understood it, the treatment of that wastewater is supported by the energy that comes in with the food waste. And this is exactly what we are talking about. And this could, it was very exciting to see this.
Okay, thank you very much. Very nice talk, very interesting. But I am a little bit confused. It was not clear for me why you call the circular economy of the water. I guess the concept is more that a biorefinery, that you can take one waste material and then you produce many other products, right? So the concept of circular economy is not clear in me in this kind of projects.
So from the circular economy definition, it's not just, so it was never meant to be just economics, right? We are basically closing the loop with this model on many different infrastructures. It's not just a biorefinery. Biorefinery is part of it. We are producing clean water. We are recovering water, and not just for drinking. We are recovering water it could be for industrial reuse, it could be for ag reuse, and it could be for drinking as well. So we are closing the water loop. So we're not just taking H2O and discharging H2O plus X or treating it and putting more energy. So we are basically closing the water loop. we are essentially closing the nutrient loop as well. So if you look at the nitrogen and phosphorus cycles, we are basically enriching the earth with more and more nitrogen and more reactive nitrogen and phosphorus. So what we are doing with this is closing the loop on those nutrients as well. Okay, and then for the organic carbon, so we have talked about water, we've talked about nutrients. What about the organic carbon? A lot of the chemicals that I'm talking about here, which we refine, and that's the biorefinery component. A lot of the chemicals that we are surrounded with, that we are part of now, or that are part of us now, where are a lot of those organic chemicals coming from? They're all coming from fossil carbon. They're all coming from carbon zero also there, but we are enriching. What we are doing is we are already part of the way there. We are just basically tapping that carbon and then biorefining them to certain endpoints, which then feed into other parts of the infrastructure. So this is the overall loop that now connects the wastewater technology, economy, and so on to many different facets. And that's what that's the circular economy here. So biorefining is only part of all of this. I focused on this because that's perhaps the most exciting. Nitrogen and phosphorus recovery is exciting, no doubt, but in terms of fundamental research discovery, perhaps we know a lot. So biorefining is exciting, but it's part of this overall circular process.
What's the purity that you obtain for your
So we produce, we don't produce a single VFA. We almost consistently, and it depends on actually the HRT, it depends on the temperature and so on. But for most, where we've kind of optimized it for between 2 and even 6 to 8 day HRT, we produce essentially a mixture of acetate, propionate, and butyrate in a ratio of 6 to 1 to 3. And that's okay. We don't, and perhaps the follow-up question is this acceptable? In many cases, we don't need a single VFA. In many cases, because the following platform, the yeast platform, is quite flexible. It can take the mixture and then go to different endpoints, and that's fine. I think there's also a lot of excitement in what happens just before the short chain VFA. I think there could be even excitement in the medium chain fatty acids, which we have not looked at. And that could mean other implications for HRT as well. But going to this new model that Professor Reva was mentioning, in some cases it might be necessary to get single components, and that's where membranes can help us. But then we have to put in energy when we put membranes.
For organic municipal solid
Yeah.
the organic fraction
Yeah.
of solid municipal waste, do you consider that it's better anaerobic fermentation or anaerobic digestion?
Oh, it depends what we want to do. So the example in the Iztapalapa campus is anaerobic digestion using USB. And so there the carbon, and so what comes in is the organic fraction of municipal solid waste, but also food organics are coming in as well into that plant and channeled through a USB for biogas. And then the biogas is, and I saw this yesterday, so I can relate this to you. It's cleaned and it's compressed, and it can be used. It can be used in the future. Okay, that's for biogas. I would still say that there's a lot of excitement in not going all the way to biogas if we can find an end application for the VFA that we produce, VFA and the products that we produce. So it can never be a technology push. There has to be a market pull for what we make. And so I don't think the question is necessarily for the municipal solid waste organic fraction, should we produce biogas or VFA or something else? It is what we need to produce. The point is with anaerobic fermentation, we can produce VFA. We know, right? I mean, fermentation is, if your digestion process goes wrong and you stop doing pH control, that's fermented, right? You stop at VFA. And you can do this, of course, more efficiently. But the point is, what is the end application? Where is the demand? And then we can decide. Chances, I mean, if the demand is for biogas, then we should make biogas. And there are communities all around the world that use biogas directly. The attractiveness of biogas is you can basically directly take a gas line from a digester and hook it up to a cook stove. And so that can be done. That is done all around the world. And so if people are happy with that, if that's all they want to do, then we should provide that to them. If there is a mature industry that can take the VFA and make something else for the community and short circuit the whole taking fossil carbon and making commodities as opposed to making commodities from waste, that's what we should do. So it depends on the application.